This is K8BYP, and like Benny Hill said, good body every morning. Big Benny Hill fan here. And we have a display from Charles out on the West Coast. He has built a dipole antenna and put a Nano VNA at the feed point with a 35-foot powered USB extension and a computer at the ground. In other words, he's repeated the experiments that I've done. This is the first time that he's done any of this. So it is extremely confusing. There's a lot going on here. And I've explained these things in great detail in my videos, but that's kind of one-sided. That doesn't give us a feel for what's happening or how to translate that to what we see here. So the key is to understand that the Nano is a VNA. It's not an impedance analyzer, it's a network analyzer, and it is a TDR, time domain reflectometer. And that's what real scientists and engineers use for antenna studies. So he's taken the right approach. That's the way they do it for real. What a TDR does is like standing in a cave and clapping your hands together. As soon as you clap your hands together, you immediately hear a very loud clap. And at twice the time related to the velocity of propagation of that sound through air for it to reach the far wall of the cave, twice that time you hear that return clap. And that's what a TDR sees when the whatever is on its output port is not the same characteristic as its port. And on that device, on most of them, it's 50 ohms, R50. If there's anything out there anywhere attached to that port that's not R50, there's going to be something coming back. What it ideally sees coming back is nothing. If it sees nothing coming back, it's a perfect termination. All the energy is forward, none's reflected, everything's happy. Since the output characteristic is 50, that assumes that the load's 50. There are three general cases as to what it sees coming back. Top left is the incident pulse in the S11 direction. Arrow to the right means forward. And the pulse is some magnitude of voltage. And it's traveling out, in this case, over a transmission line. And assuming the transmission line's R50 and there's no connectors or no discontinuities, nothing happens until the antenna. If the antenna is perfectly matched, nothing happens. The energy just goes forward. The two cases for the reflected pulse, see the arrow coming back around. On the left, an open or an R value higher than 50 is a positive step. And conversely, from the baseline, which represents R50, a step down is a short or lower resistance. The magnitude of that return pulse implies the magnitude of difference of the R value. In the case that what comes back is sloped like this, it's reactive. And this can literally be used to test components, reactive components. Assume a resistance, assume a reactance that forms a time constant, and the TDR computer measures accurately the time that it takes for that curve to sweep and probably plots it against the exponential function and can very accurately calculate reactance. It's literally the RC or RL time constant thing. That's exactly what it's doing. And from all this information, it can make assumptions of what impedance is. But it's important to understand that the VNA does not know impedance. It's a time domain instrument. It doesn't speak impedance. And these assumptions of impedance here on these data and on these graphs are because we can't inherently process these pulses in our minds. It's way easier to relate to R, X, Z, and frequency because that's what we do in electronics and electricity. So that's how we get to this point. This software has crunched this return this TDR data, and done calculations to cause this to be displayed in a format that we can just look at and say, oh, impedance is 30.9 minus 170. That's not a very pretty feed point, is it? VSWR of 20, ain't a chance that antenna will operate at 5 megahertz. That immediately tells us something useful. When I first looked at these graphs, alarm bells went off because something ain't quite look right here. Firstly, there's too much information. We don't need the plot at the lower right. That's useless. We don't care about the S21 phase. And it looks like noise anyway. See that wildly oscillating thing? That's what the TAPR VNA does when the resistive value or the impedance goes much above a couple hundred. It can't deal with it. And this is why I hammered on the point that a TDR must see a 50 ohm system. It's not valid to put some other impedance on the port. When it does, it freaks out just like that. So that data is all invalid. So that trace goes away. But these graphs are all scaled too wide. And that can be an arbitrary choice by whomever's operating the software. You can make it as wide as you want it. And it does show that peak up here in the upper right, but the data is not useful because there's no use whatsoever in 760 ohms. Completely useless. What we're looking for is down in the valley in maybe a frequency span like that rectangle. And we're looking for a minimum SWR, obviously. That's the best match. And that lives, so to speak, down inside that little circle inside the box. So that graph has to be scaled smaller by reducing the y-axis because nothing over 100 ohms is useful. And then seeing what the frequency range is where the SWR is perhaps at most 1.5, or where there's minimum reactance. The min SWR 1.34, not a scream and panic. Return loss 16 dB is not very good. It should be 40. But the elephant in the room is that this is a time domain machine, and there's a serious flaw right there. Estimated cable length 2,300 meters. There's not a prayer that that's accurate because the nano's at the feed point. There is no cable. And here's where doing this over a transmission line can cause problems. The transmission line will have discontinuities and reflections and such of its own. That's of no interest to us. Unless it's telling us a line is bad or there's a bad connector, then that's useful. But small discontinuities in a line we can't do much about, so we ignore them. So the unit could ignore small changes, and probably will, until it thinks that the pulse has reached that estimated length of 2,300 meters, which is a long time. Well, by then, with this antenna, any energy emitted has long since left the state, so that this is invalid. The problem with transmission lines, like I mentioned in a recent video, is that the losses are noticeable. And the losses affect these return pulses. If there's a lot of loss in the line, these return pulses will be a lower magnitude and appear closer to correct. They'll appear closer to the correct characteristic 50, when it's much worse than it looks. And also, if the line losses are too high and the output pulse isn't strong enough, there may be nothing come back. That's not a valid measurement. So this is why we put the measuring device right at the feed point. And that little nano is about ideal because it's very small and lightweight. And most of the weight's going to be in the USB cable. So that'll make a minimum amount that the feed point is deflected downward. But the first thing to do is to tap the time domain reflectometry button and go in and set the estimated cable length at 0 or as small as it'll go. If it's a TDR, it should have a 0 setting. It's also important with TDR devices to calibrate the port. That's done by open and short terminations. The standard procedure is like a meter-long cable for some time out and back that can be measured, and terminating that with a 50 ohm microwave load at these frequencies just makes something. But for real TDR, it's $1,000 test set to set this kind of thing up. Very expensive toys. But a meter or 3 meter long line whose propagation time is known, and then terminate it with opens and shorts, and that's part of the calibration procedure. If it isn't calibrated correctly, the magnitudes might be off, but the shape should still be pretty much correct. One of my previous videos I mentioned understanding this data by the shape of the graphs, and that we don't need the plus or minus on the reactance to tell us which one it is. We can tell by the shape of the graph. As I mentioned before, these are the shapes that can be on a frequency sweep. This shows on the left an asymptote. The vertical line, which is a resistive line, goes to infinity. From the bottom of the asymptote going to the right, that's capacitive. If we go to where the circle is at this, and the asymptote's parallel resonance in circuits. At the circle, that's a series resonance. We can see a series resonance changes impedance fairly slowly, but a parallel resonance changes extremely fast, an extremely high value. So in a series circuit at lower frequencies, capacitive reactance dominates. So the trace below the line and to the left is always capacitive, above and to the right is inductive. Important to note, the inductive trace is straight. The function for inductance is omega L. It's a straight line function. It's linear. The capacitive reactance is not a straight line. It's 1 over x. And so on a plot of x sub c vertical, capacitive reactance versus frequency on horizontal, as frequency goes down, capacitive reactance skyrockets and becomes infinity at 0. So that's why antennas are so hard to match at low frequencies. If they're inherently capacitive, which they're normally going to be, if they're close to ground, they're going to be dominantly capacitive. That reactance function climbs like a rocket. And that's what we'd expect to see here. This graph to me looks backwards. Why is that? Well, I don't know. But let's compare it. It's sweeping from 5 megahertz to 9.3. Let's compare it to my really good 40 meter dipole graph and see what it looks like. When we compare the two, the nano trace in the window on the right and a sweep from the Rig Expert 600 on my 40 meter dipole, which is darn near perfect. We see the progress to the right being a fairly gentle slope and a progress to the left going sharply up. That's the nature of that capacitive reactance going up. There's now that blue graph on the top left is the SWR, and that's a function of what's down here. The green is reactance. Let's see, red is R, green is X, blue is magnitude Z, which is a square root of R squared plus X squared. So what makes that line go up is changes in reactance and resistance to make impedance. But it's largely reactance. But notice the 40 meter dipole is not extremely broad. It's less than 1.5 to 1 across the entire 40 meter band. It doesn't really show on an SWR meter. But SWR is 6 at 1, 2, 3, 4, 5, 6, 7, 8 800 kc below 7 megahertz. So at 6.2 megahertz, the SWR is already 6. And if this graph is swept out to the same width, 6 to 8 megahertz wide, we might find that it's the same shape. In fact, we should. Of course, anything below 7 and above 7.3, we're not allowed to operate anyway. And guess why the amateur Mars thing is on the top of the 40 meter band? Look at that graph. Which side would you put it on for best antenna performance? I'd put it on the high side. So, but this is a fine result for first time through. First time through is hook everything up and get everything working and get anything displayed. Doesn't matter what it is. Then try to drill down to useful results. So throughout the lower right S21 phase, it's just oscillating wildly because the values are way too high. The upper right S11 return loss dB is kind of meaningless. That correlates with a better match. So basically all we need is the S11 mag Z and maybe an SWR plot, because we don't really care about anything else. Because what we're after, the goal of all this is to get an antenna that's perfectly flat with graphs that are just a horizontal line. The rest of this, graphs going up and down, is in areas where the antenna is useless. Then from there, it's possible to take this, excuse the cough, then this can be swept out wider in frequency to see where other frequencies are where there might be a match. And again, needs to be R50. But what you'll find, and this was clearly stated as far back as 1936 in the Radio Antenna Handbook, it ain't going to be at harmonics. There is no such thing as harmonic antennas. Hams have made that up. Doesn't exist. It's near the harmonic frequency and then some. So at this point, we're kind of at the forefront of modern antenna science. How to manipulate those other responses to put them where they want them. And that's where this gets difficult. In no case, especially in the amateur world, is it okay to start with an N-fed or an off-center fed or G5RV, which are junk, already massively screwed up, and try to improve them. We don't make a silk purse out of a sow's ear. We do what Charles is correctly doing. We build some known form of antenna like a dipole, get it right, and then try to manipulate it. Because otherwise, like the link to the paper I posted about the IEEE paper from 23 about how Ham's approach to trap dipoles is all wrong, it leads to nothing but poor performance forever. So get it working on the so-called fundamental first. It ain't rocket science. If a 40-meter dipole's big, it ain't rocket science to make a smaller dipole for 20. I just worked Europe with 8 watts on 15 meters on a 22-foot wide antenna. Total cost $10. So there's no big deal making another antenna for a higher band. So that should about cover it. Go back and make another test after setting the TDR cable length to 0 and narrow the sweep down to about a megahertz each side. And that should show that all that's needed is to correct that 63 ohms. And if one of the initial premise here is that he can't really change the height, and he knows it's not necessarily the proper height, but what's the R value? Well, it's apparently 63. Well, firstly, that's not a screaming crisis. It's not going to hurt the transmitter. Return loss of 16 minus isn't severe, but it's not right. And other radio services like citizens bands are about not getting it right. Amateur radio is about learning. If we're going to learn, we might as well get it right on 50. The way to do that, if it's 63, calculate an L network, build an L network, test and verify it with Nano, and slap it on the feed point, and it'll be perfect. So there you go. There's a tremendous amount of information, education thrown into a 20-minute video. KBYP did it.